Here in this video, let us understand the step-by-step procedures of designing of knuckle joint. In this video, we see that how the different components are designed and how to find out the dimension of different components of a knuckle joint. So here in this figure, a knuckle joint is shown to you. This knuckle joint have three parts. The first part is called the purple part, which is normally we called as fork. The middle part, which is shown by the blue color, this is called the single eye rod. This middle part, which is inserted here, is called a pin. So the connection between the fork and the single eye is made with the help of the pin. The pin is secured in its position with the help of a split pin. So here at the bottom part, you see that there should be we are using a split pin here, so that there should be a connection between the fork and the pin, and it will not come out because of this split pin. Now, as we see here, this knuckle joint is used to connect the two coaxial rods or coincide rods. Here we see that the axis of this fork and the axis of the single eye are coincide. So even in that situation, we can use this joint. And if these two axes are intersecting, even then we use this joint. Basically, intersecting means there should be chances of angular misalignment of this single eye about this vertical axis. As far as the material of this joint is concerned, we use plain carbon steel, for example, say 30 C8, whose yield tensile strength is 400 megapascal. Now, because we are making holes into the fork, into the single eye end, so there should be the stress razor points. So to account these stress razor points, we use a factor of safety of 4 to 5 for various parts of this joint basically. Now, as far as the application of this joint is concerned, this joint is used to connect tie rods in a roof trusses. This joint is also used to connect links of a suspension bridge, and this joint is also used to join the link of a bicycle chain. Now let us understand from the next slide the basic steps of designing of this knuckle joint. So it is important to discuss the construction detail of knuckle joint. So in this figure, the different links in assembled and dismantled form is shown here. So this middle portion is called the assembled view of the knuckle joint. It contains three parts: the left rod, which is having fork end, this blue part, which is called the rod with single eye end, and there is a pin which we insert in between to make the connection between the different links. This left side view, if you see here, this shows the rod with fork end, and the diameter of the rod is D here. Here the dimension is 1.2 D. Here the double eye have the outer diameter D2 and the inner diameter is D1. The thickness of this eye is 0.7 D. If we are talking about this blue part, which is called the rod with single eye, so this is the three-dimensional view here. Here the diameter is D. Here the dimension is 1.1 D, and here the thickness of this single eye is 1.25 D. The diameter of this eye is D2 and the inner diameter of this eye is D1. If we are talking about this pin is having a head, and the diameter of this head is D3. Also the diameter of this pin collar is D3. Both have the same diameter. The diameter of the pin is D1. So this is the diameter of the pin, which is having D1. With the help of this split pin, we make a tight and secure connection between the fork and the single eye. So here first we discuss the tensile failure of the rod end. So here this is the knuckle joint, and on this knuckle joint we are applying a tensile force F. So we have to first find this diameter D and this diameter D. These two diameters are same, and these are similar case when we have a cylindrical rod on which we are applying a tensile force. So when we apply a tensile force, so this rod will fail in tensile mode failure. So let us discuss it here in detail. So here, suppose this member or this rod is fail from this section, and this left side rod is failed from this section. We apply tensile load here. So if you see the cross section of this one, so this is the circular cross section, and because the force is tensile in nature, so the area resisting the tensile failure is pi by 4 d square, because d is the diameter of this one. The resisting area, that is ATR, A means area, T means in tensile mode failure, and R is the rod. So this is pi by 4 d square, where d is the diameter of this cylindrical rod on the left side as well as on the right side basically. We know the formula of tensile stress, that is sigma t is equal to load divided by area. So if you want to find out the load here, so we multiply the stress by the area. So the area is pi by 4 d square into sigma t. So here in this formula, we know the value of F, we know the value of sigma t, the only unknown is d. So we, from this equation, we find the diameter d of the rod end. Next failure is the shear failure of the pin. So this is the assembly of the knuckle joint. In this knuckle joint, we see that this green color part is called the pin. So when we apply the tensile load on this joint F, so there should be chances that this pin will fail in shear. So the next important thing is from which location the pin will fail in shear. So because here we see that this middle portion is in contact with the single eye, and this upper portion, this portion as well as this lowermost portion of this pin is in contact with the fork end. This middle portion, when we apply the tensile force, so there should be chances that this middle portion will go with the single eye on the right side, and these two upper portion, this one as well as this one, they will go with the fork end towards left side basically. So there should be chances that from these two planes the pin will slip basically, and from these two locations there should be chances that the pin will fail in shear basically. This middle portion will slide basically with this single eye. So let us discuss this in more detail here. So this is a pin whose head diameter is d3 here, and the diameter of the pin is d1. So here this blue color dotted line will show the shear areas or the shear plane or the location of the shear failure. Okay, so from this location as well as from this location it will fail in shear, and the chances that this middle portion, this middle cylindrical portion, will slide from this location in the direction of the arrow basically. So we have to find out the shear area, because this pin failed from two locations basically, one from the here and one from here. If we see in this diagram, it will fail from here as well as from here. So this is the case of double shear. So the resisting area ASP, A means area, S means shear, and P for pin. So the resisting area is twice times pi by 4 d1 square. Pi by 4 d1 square is the area, this area basically. This is the area of the pin, pi by 4 d1 square, and this twice times we have taken because this is the case of double shear failure, because the pin fails from this location as well as from this location. Now we know the formula of shear stress, that is tau should be equal to load divided by area. So the load F should be equal to the area multiplied by the shear stress, that is 2 pi by 4 d1 square into tau. So in this equation we know the values of shear stress and F. The only unknown dimension is d1. So from this equation we find the value of d1. So the next failure is the crushing failure of the pin. The pin can also fail in crushing mode. So let us see this assembly of the knuckle joint here. This green color part is called the pin. This pin can also fail in crushing. So to find out the crushing failure, let us see that where it is in contact with the single eye. So this pin is in contact from this cylindrical surface with the single eye, and from here it can fail in crushing failure basically. So if we analyze the pin, so this pin is failing in crushing mode from here, from this surface basically, and this is a cylindrical surface whose diameter is d1 and whose width is equal to b. If we see the detailed view of the single eye, or the three-dimensional view of the single eye, this is the single eye basically, and here we see that on this inner purple color cylindrical portion, this is in contact with this pin basically. This area this purple area, middle area, this is in contact with the pin. So because this area is in contact with the pin, so that this area can also fail in crushing. Okay, so this area is in contact with the pin, so that the pin can also fail in crushing mode failure basically. So how much is that area? Because this is the curved area, so we can take the projected area. So the width of this is basically with the B and the diameter is D1. So the projected area is B into D1 basically. So the resisting area which is failing in crushing, that is ACP area. C means crushing failure and P means for pin, that is B into D1. So this is the resisting area. So the crushing stress sigma C we know, that is load divided by crushing area ACP. So the load is equal to the crushing stress into crushing area. So crushing area is BD1 and the stress is sigma C. So here in this we assume that B is equal to 1.25D. This is the empirical formula between B and D. So B is taken as 1.25D. We put the value of B here, we put the value of D1 because already we have find out the value of D. The only thing we have to find out from this equation is the induced crushing stress, and we check this stress that the induced crushing stress is less than the allowable stress. If this criteria follows, then our design is safe up till here. Let us discuss the next failure of the pin, that is bending failure. The pin can also fail in bending. So if the pin is loose between the fork and the single eye, then it can be fail in bending also. Let us discuss the bending failure of the pin. Because the pin is in contact with the fork at this location as well as at this location. So from these two locations, this upper and the lower one, this is in contact with the fork end, and from this middle portion, this is in contact with the single eye. So these area will share the load basically. The total load which we are applying on this connection is F, that is tensile in nature. So let us first of all see the load distribution on the contacted area. So here this is the pin basically. The pin here is in contact with the fork as well as it is in contact with the fork here, and in the middle portion this is in contact with the single eye. So the total load is basically BF. So we have to see that how the pin is failing in bending. So this total load is F, so this middle portion load is also equal to F, which is uniformly distributed. If we assume that load as a concentrated load and divide it into the two half, or about the symmetrical about this axis basically, so this upper load is Fy2 and this total load is acting as Fy2 basically. The total width is B here because this height of this, or the you can say the thickness of the single eye is here B. So this is the B basically. So if we take the distance of this Fy2 force from this axis, this total is B, this half distance is B by 2, and we do further half of this one because this Fy2 force is acting at the middle of this upper rectangle basically. So this is B by 4. So from the axis, this Fy2 force is acting at a distance of B by 4 basically. And similarly we assume that the load which is coming from the fork end on this pin having triangular distribution. So this shows the triangular distribution force here as well as on the lower side basically. The total thickness of this fork is A. You see the total thickness is A. So here we assume that the load is 0, and here we assume that the load is maximum 1. So here the load is 0 basically, and here the load is complete load is acting here basically, and it is a triangular type of load distribution basically. Now if we finding out the total area of this triangular load distribution, this is equal to Fy2, as well as this, if we take the net load which is acted by this triangular distributed load, that is also Fy2. And if we want to find out the distance of this Fy2 from this middle axis or from the central axis basically, so this total is distance is B, so this half distance is B by 2 here. Okay, so here from here to here this distance is B by 2 basically, and this is A. And we know that for a triangular distributed load, the load is acting at a distance of 1/3 from this vertical side. So this is A basically. So from this side, this load is acting at a distance of A by 3, and the total distance of this Fy2 force is A by 3 plus B by 2 about this middle axis. So we have to take the moment about this axis, and we find out the moment is maximum at this centroidal axis basically, or the middle axis. So the bending moment M at the center of the pin, that is M, should be equal to F by 2 into A by 3 plus B by 2. This is the moment of this triangular distributed force. This force is F by 2, and we multiply this force with distance. So total distance about this centroidal axis is A by 3 plus B by 2. This is A by 3 plus B by 2. If we take the moment of this force is in the anticlockwise direction, and we assume that this moment is positive. We take the moment of this Fy2 force, and the moment of this Fy2 force is in the clockwise direction. That's why we take it with negative sign. And the distance of this Fy2 force from this middle axis, or from the centroidal axis, is Fy2 into B by 4. So if we solve these two expressions, we got the value of Fy2 in bracket A by 3 plus B by 4. And then we have to find out the value of section modulus. The section modulus, because it is a cylindrical pin, and the section modulus is pi by 32 T1 cube. And we know the formula of bending stress, that is the maximum bending stress is occurring at the center basically here of the pin. So the sigma b should be equal to m divided by z. Moment already we have find out, that is Fy2 bracket A by 3 plus B by 4. The value of z is pi by 32 D1 cube. So from this equation, we know the value of F, we know the value of A, we know the value of B, we know the value of pi by 32, we know the value of D1 cube. So from this equation, this right side term is known to us, and we have to find out the value of the induced bending stress. And we have to check that this induced bending stress should be less than the allowable bending stress. If this is the criteria, if this follow this criteria, that sigma b induced should be less than the sigma b allowable, then up to here our design is safe basically. Here the next failure is the tensile failure of single eye basically. So here we see that this blue color part is called the single eye rod here basically, and the pin is inserted between this to make a joint between fork and the single eye rod basically. The single eye rod can also fail in tensile failure at the weakest section. You see that we insert the pin here in the single eye. So here we are making a hole in the single eye basically. When we make the hole in this single eye, the single eye is weak at that location basically, because the area is minimum and the resisting area is minimum here. If we see the three-dimensional view of the single eye, so this is the three-dimensional view of the single eye here. Here if we see that here we are making a hole to insert the pin basically. Okay, so this area is basically be minimum one, so that there should be chances that when we apply the load here F on this one, so this area will resist the deformation or the movement. Basically what is happening, a resisting force is also acting on this one, and there should be chances that from this x-axis location, from the weakest section, it will fail in basically be in the tensile mode basically. So if we properly analyze this area more in detail, so this is that area. We see that this pin is in contact with this curved area whose inner diameter is d1 and whose height is equal to b, or the width is equal to b. So what is happening basically, when this force is applying on this one, what is happening, that this is because this area is resist the tensile failure. This sided blue color sided portion will resist the tensile failure. So how much is that area basically? This total outer diameter is d2, the inner diameter is d1. So this d2 minus d1 is the thickness of this both the strip basically, and multiplied by b basically. So the total area is d2 minus d1 into b, which is the blue color sided portion, which normally we resist the tensile failure of the single eye basically. So the total resisting area should be equal to AT SE. A is the area, T is in tensile failure, SE means single eye, that is B into D2 minus D1 basically. This is this blue color sided portion. So we can find out this area, that is B D2 minus D1. So we know the tensile stress should be equal to load divided by the tensile resisting area. So tensile resisting area, if we multiply by the stress, we got the value of the load here. So the load should be equal to B, this D2 minus D1 is the area, and sigma T is the tensile stress. So in this equation we know the values of F, B, D2 and D1. So from this equation we find out the value of the induced tensile stress. If the induced tensile stress is less than the allowable tensile stress, then our design is safe up to here. If suppose the tensile stress which is induced inside the metal is more than the allowable stress, then we have to increase the value of the D2. So the one way to achieve this is we put the value of F in this equation, we put the value of B in this equation, we put the value of D1 in this equation, we put the value of sigma 2 allowable here and find out the value of D2 from this equation. This single eye and rod can also fail in shear. So this is the pin basically, and the pin is in contact with the single eye here, and when we apply the value of the force F here, so there should be chances that this portion of the single eye can fail in shear. Let us see the three-dimensional view of the single eye. This is the three-dimensional view of the single eye here. So here we see that this purple color line or this purple color area which is in contact with the pin can also fail in shear. This can fail in shear from this green color section YY, and this is the Y here, this is Y here. So from this location this can fail in shear, means this much of the portion of the single eye can slide outside basically. Okay, so that can fail in shear. Let us analyze this area in more detail. So here we see that this is a single eye, and as we are talking that this area from the section YY can slide outside. So let us see this here, this complete area, this is Y section here, Y section here. So from this YY section, this area, when we apply a force F here, this can slide outside basically. Now this sided portion, this vertical sided portion is the area which fail in shear basically. So there are two areas, one from this side and other from the back side basically, having equal in magnitude. So these two areas can fail in shear mode basically. Now we have to find out this value. The outer diameter is D2 and the inner diameter is D1. So this thickness is D2 minus D1 divided by half basically, and so this thickness is D2 minus D1 divided by half. Same, this thickness is D2 minus D1 divided by half, and this is the value of the V. So one side area is D2 minus D1 divided by 2 into B, this side, and D2 minus D1 divided by half into B is the area on this side. So because this is the case of double failure, so we can add these two areas. So when we add these two areas, we got the value of D2 minus D1 into B. So here let us see that how much is the resisting area in shear. So resisting area is ASSC, means A is the area, S is in shear mode failure, and SE means for single eye. This is 2 times D2 minus D1 divided by B. D2 minus D1 divided by 2 is this thickness of this strip, okay, from here as well as from here, and B is the height of this one. So this area is D2 minus D1 divided by 2 into B, because this area fail in double shear, that's why we multiplied by 2 here. So the 2 will cancel out, so we got D2 minus D1 into B. So the shear stress should be equal to load divided by shear area. So the load should be equal to shear area multiplied by the shear stress. So shear area is D2 minus D1 into B into tau. So we see in this equation, we know the values of F, D2, D1 and B. So from here we find the value of tau induced and check that this tau induced value should be less than the tau allowable value. If this criteria follows, then our design is safe up to here. Next failure is the crushing failure of single eye. So again, this blue color part is called the single eye rod. This is in contact with the pin at this location, and here we see that this area is in contact with the pin. Okay, so here this area is in contact with the pin, and this is a cylindrical area basically. If we see the three-dimensional view of the single eye, this is this area basically. So we are talking about this purple color area which is failing in crushing basically. So here this is the curved area whose inner diameter is D1 and basically the height is B basically. Let us discuss this area in more detail here. So we see that here this cylindrical portion, this purple color shaded portion is in contact with the pin. So when this area is in contact with the pin, so this area can also fail in crushing basically. So how much is this area? This width or the thickness of the single eye is B here, and this diameter is d1. If we take the projected area basically, so this projected area is look like a rectangle whose depth is equal to b basically, as whose width is equal to d1. So this total area is how much? This area is d1 into b basically. So this is the projected area of this curved portion whose diameter is d1 as whose thickness is equal to b basically, and this area is fails in crushing basically. So the resisting area ACSE area, C means crushing failure, SC means for single eye, that is d1 into b. This is this projected area basically, and this is d1 into b. So the crushing stress would be equal to load divided by crushing area here. So the load is equal to, we multiply this crushing area with this crushing stress. So the crushing area is d1 into b. So the load F is equal to d1 into b is the crushing area multiplied by sigma c. In this equation we know the values of F, d1 and b, and from this equation we have to find the value of sigma c induced and check that the sigma c induced value should be less than the sigma c allowable. If this criteria follow, then here up to here our design is completely safe. Next failure is the tensile failure of the fork or double end eye. So this purple color part is called the fork end rod basically. Okay, here it is a rod portion, and on the right side we have this fork basically, or we call it at a double eye, and this double eye is in contact with the pin at this upper portion as well as at this lower portion basically. So if you see the three-dimensional view of this fork rod basically, so this is of this kind. Here the diameter is d, and here if you see the outer diameter is d2 of this eye basically, and the inner diameter is d1, and there are two eye, that's why we call this end as a double eye end basically, and this is also in the form of a fork basically. The thickness of this is A is equal to 0.75 d basically. So when we apply the tensile load here, so there should be chances that from here, because we insert the pin and make a circular hole inside the fork. So you see that there are two circular holes, one is on the upper eye, other is on the lower eye basically. So from here this is having the weakest section, so this fork will fail from the weakest section under tensile mode basically. So what is happening when we apply a load, so this pin will resist basically its movement further. So because of this movement, what is happening from this XX section, it will fail in tensile mode. If we see the detailed view of this one, this single eye, if we consider here, the single eye from this middle section will be divided into two halves basically. This is the left half portion, this is the right half portion. Similarly on the bottom side here, this also fail from this section XX. So this is the section XX. So this left portion is remain with the fork, and this right portion will go towards the right side basically, and it will normally be fail basically. So this sided portion, this portion which is weakest basically, and that is also failing in tensile mode, as from the top eye as well as on the bottom eye basically. So if we finding out this sided area, so this outer diameter is d2 and the inner diameter is d1, and this height of this or thickness we call of this double eye is basically BA. So the total area is d2 minus d1 into a on one side, and the same area we have on the other side, that is d2 minus d1 into a. So we have to add these two area, because these two area will resist the tensile failure. So the total resisting area AT F oblique D means A means area, which T means tensile failure, F means fork end or the double eye end side, that should be equal to twice times d2 minus d1 into a. This is the net resisting area. d2 minus d1 into a is the resisting area on single eye, because this diameter is d2, this inner diameter is d1, and this sided portion is nothing but d2 minus d1 is this thickness. Okay, this is both the thickness here and multiplied by a basically. So this is d2 minus d1 into a. We multiplied by 2 because there are two resisting area, one on the upper eye as well as on the lower eye basically. We know the value of the tensile stress. The tensile stress sigma 2 should be equal to load divided by the tensile area failure. So from here the load should be equal to sigma t stress multiplied by the area resisting tensile failure. So resisting area is 2 bracket d2 minus d1 into a into sigma t. So in this equation we know the values of f, d2, d1 and a. So from this equation we find the value of sigma t induced. Okay, and check that the sigma 2 induced value should be less than the sigma t allowable stress. If this criteria follows, then our design is safe up to here. So next failure is the shear failure of the fork or the double eye. So here we see that this purple color part is called the fork end, and this blue color part is called the single eye, and we insert a pin in between. So we have to see that which portion of the fork is in contact with the pin. So we see here this portion as well as this portion, these both portions are in contact with the fork basically. So these, from these locations, it can also fail in shear basically. So if we see the three-dimensional view of the fork and analyze this area into more detail, so we see the three-dimensional view of this fork here. So this is the three-dimensional view of the fork here. So here we see that at this location here, as well as on this lower eye at this portion, this pin is in contact with these two eyes here. Okay, and when we apply the load F here, so these area resist the deformation or the failure basically, or resist the movement basically, and they fail in shear. So from the location y by, from this location, as well as on the lower eye from this location y by, okay, they will fail in shear basically. So what is happening when the force is applied here? So this portion will slide outside from the upper eye, and this portion from this location will also slide from the outside. So let us see this area, how it is happening basically, how this area will slide outside. So here we see that this is the suppose top eye or the upper eye basically. So when the force is applied here, so what is happening, this will slide outside from y by location. So let us see, this is the y by location here, and this portion, when we apply the force on this one, this will slide outside. Now let us understand how much is this area. This is the case of double shear, because this is failing at two locations, one from the front side, other from the back side basically. So how much is this area? This diameter is d2 and the inner diameter is d1 basically. So this thickness of this strip is d2 minus d1 divided by half into a basically. So this is the area on one side, the same area we have on the back side. So we do the twice of this area. So because this is the case of double shear, so if you want to find out the resisting area, that is ASF oblique DE, so this is twice times d2 minus d1 divided by half into a. This is the area on upper eye, because this dimension is d2 minus d1 by half into a. This dimension also d2 minus d1 by half into a. The total area is d2 minus d1 divided by half into a into twice basically. Because there are two eyes, a similar kind of failure also happening on the lower eye, so we multiply it by 2, because there are two eyes basically. So we multiply it by 2 here. So this 2 will cancel out. The total area is 2 d2 minus d1 into a basically. So this is the net resisting area. So the shear stress, we know that this is load divided by the resisting area in shear. So the load should be equal to, you multiply the shear stress with this area. So the load F is equal to twice times d2 minus d1 into a into tau. So from this equation we know the value of F, d2, d1 and a. So from this equation we find the value of induced shear stress, and check that this induced shear stress would be less than the allowable shear stress. If this criteria follow, so our design is safe up to here basically. If suppose the tau induced should be more than the tau allowable value, then we have to increase the thickness of the fork A basically. Or one way to do this is that we put the value of F in this equation, we put the value of d2, we put the value of d1, and we put the value of allowable shear stress, and find out the value of the A or the thickness of the fork from this equation. The fork or double eye can also fail in crushing mode. So the next failure is the crushing failure of the fork or the double eye. Again, we see that this fork is in contact with the pin at the upper portion here, as well as on this lower portion here. Because this is in contact, because to find out the crushing failure, we have to see that which area of the pin is in contact with the fork, the upper eye as well as of the lower eye basically. So let us see the three-dimensional view of this fork here. This is the three-dimensional view of the fork. So here we see that this portion, which is between the section X and X, this is in contact with the pin here on this upper eye. On the lower eye also, on this section X, this is in contact with the pin basically. So when this area is in contact, so this is a cylindrical area, okay, whose inner diameter is d1 and whose thickness would be equal to a on the upper as well on the lower eye. So because this cylindrical area is in contact with the pin, so this area can also fail in crushing basically. Let us analyze this area here basically. So this red color portion or this red color patch or this red color area, that this area is in contact with the pin, okay, and this area is the area of the fork or the upper eye which is in contact with the pin here. Similarly, we have the similar area. This is this red color area. This is in contact with the pin, or this is the area of the fork basically. So this red color patch area or this red area here as well as here, they can also fail in crushing basically. So we have this, the inner diameter is d1 here and this height is basically ba. So the projected area of this curved portion is d1 into a basically. So d1 into a is the projected area for the upper eye as well as for this lower eye basically. So the total area which is against crushing is twice times d1 into a. So resisting area ACF oblique D, area which is failing in crushing. F is for fork or for double eye basically, just twice times d1 into a, because d1 into a is the projected area of this curved portion whose internal diameter is d1 and whose height should be equal to a basically. And this is the, because there are double area which resists this crushing failure, so we do the twice of this area, one on the upper one on the upper eye and other on the lower eye basically. And the crushing stress would be equal to load divided by the crushing area. So the load F should be equal to twice times d1 into a into sigma c, this is the crushing area, multiplied by the crushing stress basically. So in this equation we know the values of F, d1 and a. The only value of sigma c we have to find from this equation, and the sigma c value is the induced stress. So this induced stress value, when we find out, this would be less than the allowable crushing stress basically. If this criteria follow, then our design is safe up till here basically. Thanks for watching this video on knuckle joint design. So in this complete design we see how to design the knuckle joint, and we discuss the step-by-step procedures in the easiest way so that you can easily understand. We can also support the different failure modes with the help of diagram so that you can easily understand them. If you like this video, please like, subscribe, share and comment. Thank you very much.